Hello everybody, and welcome to another geometry lesson. Today we're taking a look at section 7.3, proving quadrilaterals are parallelograms. So last section is going to have a pretty big impact on this one. If I show you a shape, how could you prove that it's a parallelogram? Well, there's a lot of different ways to do it, as it turns out, based on what we learned last class. We know that parallelograms all have parallel sides, for instance, or that their opposite sides are the same, or that their diagonals bisect each other. There's a whole bunch that we learned. Today, we are actually going to apply them in practice, in proofs. So let's take a look real quick at some of these definitions, because they're going to look familiar. The first is the parallelogram opposite sides converse. What's a converse? Well, besides being a shoe company, a converse is a theory that is flipped backwards. It's almost like the opposite. So if you still have your section 7.2 notes, you can already make the converse just based off of what you see. In general, here is the deal. We've got a shape. We don't know that it's a parallelogram, but we think it might be. We know that if the opposite sides of a parallelogram are congruent, if both pairs of opposite sides are congruent to each other, then the shape has to be a parallelogram. Cool. So all these theorems are going to start off the same way. If a quadrilateral, which I'm going to abbreviate as if a quad, I hope you'll forgive me. If a quadrilateral has both pairs of opposite sides as congruent, then it's a parallelogram, obviously. So basically, if you know that all the sides are congruent to their opposite sides, you know the shape you're looking at is a parallelogram. Same with the opposite angles, as it turns out. If both pairs of opposite angles in a quadrilateral are congruent, then it's a parallelogram. That's the parallelogram opposite angles converse. It says if you already know the angles are congruent, then you know it's a parallelogram. The next theorem is actually something a bit new. We haven't talked about this one before, but it goes something like this. You have a shape that you suspect is a parallelogram, and you know the following. You know that one pair of angles, or one pair of sides, is congruent, but not the other necessarily. And you know that those two sides are also parallel. They've got to be both parallel and congruent. But believe it or not, just by knowing that little bit of information on one pair of sides, the parallelogram is a parallelogram. It has to do with the alternate interior angles of the parallelogram. It has a lot to do with the consecutive angles of a parallelogram. It deals with all of this. But the idea is, if one pair, just one pair of opposite sides in a quadrilateral are congruent and parallel, then it's a parallelogram. Very nice, last one. The last theorem involves the diagonals of a parallelogram. If you may recall, the parallelogram's diagonals are the lines that connect the opposite vertices. If you know that those diagonals bisect each other, you know that you're dealing with a parallelogram. If both diagonals of a quadrilateral bisect each other, then it's a parallelogram. Once again. Nice. For future reference, all of these theorems are down here at the bottom with diagrams showing them. So now we have 5 ways to say that something is a parallelogram. If both pairs of opposite sides are parallel, bam, it's a parallelogram. If both pairs of opposite sides are congruent, bam, parallelogram opposite sides converse says it's a parallelogram. Parallelogram opposite angles converse says the same happens if the angles opposite each other are congruent. The sides parallel and congruent theorem says that you only need one pair of sides, but if you know that, you're good to go. Last off, diagonals bisecting each other by the parallelogram diagonals converse tells you that, yes, indeed, it's a parallelogram. Let's flip the page and take a look at some of these examples. Example 1 is asking us to find what values of x and y make the figures below parallelograms. We have to also state a theorem that we use to find our answer. So we don't know what values of x and y we're going to be using. We could use any values. We could use 10, we could use 50, we could use -2. But only one value is actually going to make this shape a parallelogram. Here's how we do it. We know the different sides of this parallelogram, right? Well, according to the parallelogram opposite sides converse, if it's a parallelogram, these two sides have to be congruent to each other, and these two sides have to be congruent to each other. In other words, due to the parallelogram opposite sides converse, that's the theorem we're using, we say that x plus 9 has to equal 2x minus 1, and that x plus 7 has to equal y. This equation can't be solved just yet. There's 2 variables, and you can't solve an equation if you have 2 variables. But we can solve this one. We start by subtracting x from both sides to get 9 equals x minus 1. We can add 1 to both sides to get x equals 10. So we've solved for the x value that makes this a parallelogram. If we know x is 10, and x plus 7 equals y, then 10 plus 7 equals y. And 10 plus 7 is 17. We can use similar logic on the next couple of problems. So take a second and try out problems B and C. Pause the video, and I'll put the answers up on the screen in just a moment. How'd you do? These are the values that will make the following shapes parallelograms. Next on the list, we have example 2, which is write a proof given the very limited information that we have. Here's the deal. We're trying to see if ABCD is a parallelogram, but all we know is this. Angle ADB, so this angle that I've marked in bolded purple here, is congruent to angle CBD, this angle that I've also bolded in purple up here. Additionally, we know that these two sides, AD and CB, are congruent. And somehow we need to show that this is a parallelogram. Well, we always know a good start is to just list off our givens. So let's do that. ADB is congruent to CBD, and AD is congruent to CB. Cool. Those are some free points for us right there. From here, though, we're a little bit stuck. There's a couple pieces of information that we could utilize. We could, for instance, say that BD is congruent to DB. That might get us somewhere. And in fact, it'll help us find that two triangles are congruent. You could say that angle A is congruent to angle C, but we don't know that yet. It would have to already be a parallelogram to do that. So that's off the record. We can't do that. So what can we do? Well, we do know one thing. We know that these angles look to be on either side of a transversal. In fact, if I draw out the lines here, maybe tilt it sideways to help it come along better, aren't these alternate interior angles? You may recall from Unit 3 that if you know that the two alternate interior angles are congruent, then the lines that they're on have to be parallel. So that is actually going to be the shortest way to prove this. We know that AD and CB have to be parallel due to the alternate interior angles converse. The converse is what says the lines are parallel. And wait a second. We've got these congruency markings here. We've got these parallel markings here. Isn't there a theorem that says if the opposite sides are parallel and congruent, then it's a parallelogram? ABCD is a parallelogram due to the opposite sides parallel and congruent theorem. Sorry, I didn't mean to draw a squiggle through my parallel lines. But that's the theorem right here. Opposite sides parallel and congruent theorem. Fun. So that's how we would approach this proof. Last, most certainly not least, we want to show that a shape is a parallelogram. When you have a shape that's on a graph, there are some things that we know how to find, and there are some things that we don't. We could try to find the angle measures of all of these, but that doesn't make sense to us here. There's no way to find those angle measures at this point in the semester, maybe later. We could try to find the diagonals of the shape, but the diagonals don't exist. Let's not complicate this. What we can do is we can find if the opposite sides are parallel, if the opposite sides are congruent, or, sort of like how we did up here, a combination of the two on one edge. Those three theorems can be used to show that something is a parallelogram on a graph. These are theorems 1, which is the definition of a parallelogram. It says all sides must be parallel. 2, the opposite sides converse, which says if we can find the lengths of all the sides and compare them, if it's two pairs of the same length, it's congruent. Or 4, which is a combination. We show that one pair of sides is both parallel and congruent. To save on time, I'm going to do problem number 4, or theory number 4, so that you can see how to find their congruent and how to find their parallel. So let's do that. We have to show that any one side of this quadrilateral is both parallel and congruent. So how do we show the two sides are parallel? We know that two things are parallel if their slopes are the same. So all we need to do is find the slope of AB and the slope of CD and compare them. The slope from A to B, I go up 2 over 5, it's 2/5. The slope from D to C is up 2 over 5, it's 2/5. Cool! These two lines are parallel. That does not mean they're necessarily congruent, but it does mean this. It means that AB is parallel to CD. How do we find that two sides are congruent? Well, we would need to show that their lengths are the same. In other words, the distance from A to B has to be the same as the distance from C to D. So we can use the distance formula. The distance of anything, any 2 points, is the square root of x2 minus x1 squared plus y2 minus y1 squared. Good. From here, we can find the distance from A to B and the distance from C to D. From A to B, we just plug in all of these points. So the two x values are -3 and 2. -3 minus 2 squared plus 3 and 5 are the two y values, so 3 minus 5 squared. We end up getting, after you do all of this, that this is 25, plus this here is going to be 4, the square root of 29. Cool. The distance from A to B is the square root of 29. Let's do C and D as well. So we repeat the process, take the square root of the two x values. These are a little easier because we have a 0, 0, so it's 0 minus 5 squared plus 0 minus 2 squared. That's 25, that's 4. Hey, square root of 29, they're the same. That means that AB, whoops, don't want to say parallel, AB is congruent to CD. So we can say, as our final answer, by the opposite sides parallel and congruent theorem, ABCD is a parallelogram. Done. That is it for our notes, everybody. Thank you so much for listening, and have a fantastic rest of your day.